Hello and welcome to another episode of the Oxford Online Maths Club. My name is James, I'm the Admissions and Outreach Coordinator for Maths at Oxford, and I'm joined today by one of our first year students, Lucy.
Hi.
Lucy's going to join us today to talk about some mathematics that Lucy's learning on the university course in first year. But I feel like we should also say that a year ago, before Lucy was in first year, Lucy, what were you doing on Thursday afternoons a year ago?
I don't know what I was doing at exactly 5 p.m. as well.
Exactly 5 p.m. Yeah, so Lucy watched the Maths Club and Math Livestream stuff a year ago,
Yeah.
um, and is now one of our students, and is now on the show to talk about some maths. So it's coming up. People in chat are saying hi to Lucy. One person just says,
Hello.
"OMG, it's Lucy."
Oh,
So
hi.
I guess celebrity in that sense. You might have also seen Lucy on the Oxford Mathematics channel with some sort of vlog content on the maths course, or on Lucy's YouTube channel with
Yeah.
more maths content. Right, okay, let's do the bit at the start. Coming up today, we've got double integration. You've met integration, Lucy's going to show us double integration. Also on the show, we've got a probability question with dice, any excuse to get dice back onto the live stream again. And I also want people to say hi to Charlie in the chat. Charlie is one of our first year students. It's her first time helping out with chat. I haven't told Charlie I was going to do this. Charlie is in chat answering questions and helping out over there. Everyone say hi to Charlie as well. Also Christian is here, but Christian was here last week as well, so sorry Christian. Okay, cool. Right, let's see what happens in chat now. Okay, I think that's my. Oh yes, I always forget this slide. Further reading is posted on Friday to the Maths Club website, which is maths.ox.ac.uk/r/CLUB. Except last week I forgot to do it on Friday. Sorry if anybody noticed that. It came out on Monday. I'm going to try really hard to remember tomorrow and put further reading and links and more maths related to the stuff from the live stream should appear on the website on Friday, if I remember. Okay, right, that's the plan. In chat, who's in chat today? Beth and Alfie and an anonymous person and Kelsar in chat have all said hi to Charlie. I can see other people in there as well. If you want to join in with the live chat that's zooming past on screen at the moment over there, you can go to slido.com/OOMC. And Molly has reminded me that I can turn on replies, which I've now done. Thank you, Molly, for the reminder. Okay, we're using Slido chat because it's got replies, which let our current students, Christine and Charlie, in chat today talk to people, and also because you can be anonymous or put in your name if you want to. Cool, right, okay, I'm going to switch to Lucy's slides, actually like this, and I think, Lucy, it's over to you. What are we integrating first?
We are trying to find a region bounded by three of these things. So we have a y equals square root of x, a y equals x minus 2, and an x-axis. So we should be able to do this using A-level methods. So if I just do a quick graph sketch here, and if I draw on the y equals square root of x, so I think you might have seen this before. So if you just think of it as rotating, it would look a bit like the x squared. So like that. And then the x minus 2 would look something like that. And then because we're bounding with the x-axis as well, then it will be this area. So I think you should be able to do that using your knowledge of integration. So should I give them some time to do that?
Let's give them a moment to tell us whether they know how to do this with A-level methods. I see you've put
Yeah.
A-level method on the board.
A-level method,
If
hopefully.
people are watching in year 12 or year 13, they might, I hope, have seen how to integrate square root of x, which is the same thing as x to the 1/2. If they've seen how to integrate really anything, then hopefully they've seen x to the 1/2. If you're watching, if you're in year 10 or year 11 and you haven't seen integration yet, then hey, you're going to learn how to integrate some functions of x today. Learn how to find areas underneath curves.
It's one of the best
What does
topics.
chat think of this? Chat wants to know if they're going to get a 9 in GCSE maths. The maths we're about to do is not GCSE maths. It's unrelated to GCSE maths. But being interested in maths might be a good way to get along with GCSEs as well. Okay, chat's gone really quiet. Oh no, there's a bit of lag between us saying stuff on the stream. I have to remember, a bit of lag between us saying stuff or drawing things and people joining in chat. Someone who's in year 12 and hasn't learned this yet. I guess if you were in year 12, you've only had about 4 months of year 12 maths, and maybe you still had some GCSE maths to catch up with. There's a method for integrating functions like this. There's some rule about what happens when you integrate powers of x to find the area underneath curves. Alfie's got an idea, which is to integrate and subtract a triangle. Does that sound like the A-level method to you, Lucy?
That sounds like a great A-level method. So by integrating, let's look at the integration first. So we'll consider this graph. So this is y equals square root of x. And then what Alfie mentioned in the chat is that, so by integrating, you will get this entire area. So let's change color. We will get this entire area here. And then we can subtract this little triangle because that's been removed. So if I set up the integration, we'll be integrating between x equals 0, so like down here, and then here, which would be x equals 4, and then the x to the power of a half, and then dx. And yeah, hopefully.
Brilliant. Okay, so someone in chat has joined in to say they're in year 12 and do know how to integrate x to the 1/2 between those. So there's some rule that people learn in possibly at some point in year 12 for how you actually work out that integral from x equals 0 up to x equals 4 of x to the 1/2 with respect to x. Do you want to remind people of how that works?
Okay, yeah. So the general rule for integrating is if you integrate something along the lines of like x to the power of c, so that's just like a polynomial, and then the integration of that would be, so you add 1 to the power, so x to the power of c plus 1, and then you divide. Have I gone too far that way?
Oh, yeah, I've cropped your slides off very slightly, sorry.
Okay, no, don't worry. No. So x to the power of c, if we integrate that, that would become, we add 1 to the c, so x to the power of c plus 1, and then we divide by it, so 1 over c plus 1. So if you can have a go at this, and then if we add the limits, we basically substitute it when x is equal to 4, because that's the upper one, and then we minus when x is equal to 2, 0 even. So maybe let chat have a go at like working that out and see what they get.
Cool. I am going to try and resize this because the way I've set it up at the moment, chat is a bit over the top of some of the maths. Okay, let's make that smaller. In a bit. What we're watching now is live stream curation setup. Let's try that. Okay, it's a little bit better. I put black bars on it. Oh, and we've gone silent. Possibly. Okay, so we've got an integral. There's some rule about how you integrate powers of x. X to the c integrates to the function x to the c plus 1 over c plus 1. And if you put in the limits, the rule is you put the top limit and you subtract the thing that you get when you put in the bottom limits. So that'll give us the, I think, green area in the picture.
Yeah.
The overall area underneath root x. And okay, if we do that, then I think c is 1/2. So the thing on the bottom is 3 over 2, and this is x to the 3 over 2. I need to plug in 4 and plug in 0. Oh, here we go. Brilliant. Okay, so plug in 4 and plug in 0 to work out that area. And that gives us the green area underneath the x to the half curve. Oh, hello. There's a first-time viewer in chat called Zero Smile. It says, can someone explain real quick how this live thing works? We're live. Welcome to the internet. We're doing maths. What we're doing, we're trying to integrate some function. We're trying to find this area with region R bounded by particular functions. Cool. Oh, people are replying in chat. I like it when people help out.
Oh, someone can't hear us.
I think it's okay. Most people have not said that in chat.
Okay.
Okay, how's it going? We've got a number. We've got 16 over 3 for the green area underneath that square root x.
Yeah, we have 16 over 3 for the green area. So as someone suggested before, we will maybe find the orange area now. So this is like the little triangle. So we know that this has coordinate 4, 2. This has coordinate 2, 2, 0. And then over here we have a 4, 4, 0. So this is just like a triangle. You should all be able to work out the area of a triangle. So that would just be a half times 2 times 2. No, a half times 2 times 2, which is just equal to 2. So by doing this, we have a 16/3, which was the green area, and then minus the 2 from the triangle. So then overall, we get a 10/3 for the area bounded, the region R that they asked you for.
Cool, brilliant. Okay, 10/3, A-level method. If you're an A-level student who's already seen integration, then hopefully this sort of integration, integrating x to the half, by turning it into x to the constant and using the rule for integrating x to the c, hopefully that's something that you've seen before. If you're in year 11, then hey, there's this magic rule you learn at A-level for what the area is underneath different powers of x. Some rule for working out those areas that we've just gone through at lightning speed. Welcome to A-level revision, I guess. So that's the A-level way of working this out. I think this is a past math question, by the way. I think we've used this as one of the multiple choice questions on the math submissions test at some point. Now this is not the math live stream, but at some point, if you're interested in more questions that you could do with A-level methods that are a bit tricky, then there's something called the mathematics submissions test out there for people to try. So somebody's just asked, is this something you might see in an interview? It's something you might see in the math submissions test before the interview, but maybe not this question anymore.
The math's so scary.
Is this in AP Calculus BC? Says somebody in chat. This is, I think, one of the first things in AP Calculus BC. If you learn calculus, then you'll learn about differentiation and integration. Integration to find areas. You'll learn about integrating powers of x. Okay.
Should we move on to the cool university method is the one we're going to do next. So I'll just remind you of like the sketch, something like that. And then we're trying to find this area. So if we try and like split it down like this, so we're trying to split it into many little vertical strips. So if you've done integration before, then you've probably seen something like this. So we're basically going to consider one of these like little strips, and then we'll see how we can like get from one strip to lots of strips. So if we just look at one of these strips, it's bounded by the upper bound and the lower. So if we look at, for example, this strip, let's say this green strip here, then it's bounded by this one as the upper and then this one as the lower. So you can see that the lower bound would be y equals 0, and then the upper bound would be the y equals square root of x. And then if you were to split it into this other region, let's make this purple, this one, that would have slightly different bounds. So the lower bound would be, this time it would be this line. So that would be the y equals x minus 2. And then the upper bound would be the same because it's still across here. So that would be y equals square root of x. So let's just look at, so we have the green area and the purple area. If we look at the purple area first, since we're already on purple, then we have something that looks a bit like this. So if we take one of these little strips, then we can like almost set up an integration just for one of the strips. So if we go from the upper, so we take the integral, this will be, because it's going vertically, then this will be something, it will be like a dx. And because it's a dx, then we have to take the limits as x equals something and then x equals something. So we already know from here what the bound is. So we just have to do a quick like reshuffle to make it an x, so rearrange it to get the lower bound as x equals y plus 2, and then the upper bound as x equals y squared. So, and we're just going to integrate 1 here. So that forms one of our little strips here. And then because we don't have just one, we have lots. So we're going to take a lot more. And in order to get that, we have to form a second integral. So that would be another integral there. So we have a dy there, because we've already done the dx, and we're taking these strips between 2 points. So y equals, so we would take this between this one and this one. So over here we have a y equals 2, and then over here we have a y equals 4. So we can, now we've set it up, we've done the really tricky part. So we've set it up now. So we're going to try and compute this. So because we're starting with, we go from inside and then we work our way out. So if we take the integral between y equals 2 and y equals 4, that can just stay the same, as well as the dy. And then in the middle, we can integrate this. So we have a 1, which we're integrating with respect to x. So for those of you who have seen integration, that is just this integral. So that will just be x. And then if we put in the limits, we will have an x equals y squared, and then an x equals y plus 2, which I have made myself run out of space here. So if we rub this out, we've dealt with that already. We will plug it in. So we'll just deal with the y. So y equals 2, y equals 4. And then we'd substitute in the x equals y squared, the x equals y plus 2. So then we'll end up with a y squared. And then we're taking away this y and then take away 2. Because, yeah, you're taking away the lower bound. So then that's a dy. So as you can see, we've magically transformed like an integral with respect to x into an integral with respect to y. So we have, because of the limits, so like the limits link the two together. So if we integrate this now, we're integrating dy, so with respect to y. So this would look something like y cubed, a third y cubed, then a minus y squared, a half y squared, and then minus 2y. And then we're substituting in y equals 4, and then y equals 2, and then hopefully a number will come out, like a nice number.
Do you want to go, sorry, do you want to just briefly, before we plug the numbers in and rub everything out, I've turned off chat so that we can see stuff there was some stuff underneath chat. If people are wondering where chat's gone, I just switched it off so that we can see. Chat's still happening though. And we think maybe you've done horizontal strips. I think I agree with the maths you've written down, but I think that maybe this is the horizontal strips one. Do we maybe want, because you've got y's 2 to 4, I think I'm trying to match up your picture with the maths that you've written down, but I think it's going on. Can we point at? Don't worry. Can we point at the bit? I want to go back to the bit where you said we're going to integrate 1 with this dx dy, because I feel like I want to make more of a point of that, because this is the sort of weird thing that we've just been doing at university. I'm going to have a go at drawing some things. Here's my attempt. So I think the kind of new idea is that we can do 2 integrals. This is some general trick for finding areas, where what I really want to do is add up lots of tiny contributions. So you can think about this shape that we've got as being made up of lots of little rectangles. This is the kind of thing that they teach you when you learn about what integration is, right? You learn that integration is defined in terms of adding together lots and lots of tiny rectangles. But each of those rectangles, you could think of that rectangle as being made up of lots and lots of tiny squares, with the squares going between some limits. Now that sounds like a bit of a mad idea, right? Because we've got these little squares to add up, and we're now doing twice as much work because we're integrating the little squares. We're going to do an integral to work out how many little squares we've got in the column, and then we're going to add up all of the columns. This is what a double integral is going to involve doing: 2 integrals, one to add up all of the little squares that way, and then one to add up the rectangles. Which maybe sounds like a complicated way of working out areas, but it's really flexible. What do I want? I don't want that, do I? I want this. So it's really flexible because it lets us work with more complicated edges or more complicated shapes going on. Okay, I'm gonna try really hard to write down the thing that I think we should have written down, Lucy. I'm gonna have a go.
Yeah.
My turn. Okay.
I can see it as well.
So,
I've taken the horizontal
here's my
strip.
inside bracket thing. Inside bracket. Oh, that's a weird shaped bracket. Can I undo in here? I cannot undo in here. Here's my inside bracket thing. Now on the inside, I've got to try and add together these little squares. Each little square has got area, little dx width and a little dy height. That's how big a tiny little square is. The squares are tiny. They're little squares, dx by dy. And I want to add them. I suppose I want to add together all of these ones with different y values. So I want to do this integral inside. I think I want to add together the different ones with respect to y. Doing the little vertical integral to add them together. And then when I've done that, I will add all of those up with respect to x, I think. Does that make sense? So I've got y on the top. I haven't got an idea what this y at the top. I might need to write down what that actually is. Y at the bottom. And then I want to add all of those rectangles together to add together x all the way on the left, all the way up to x all the way on the right. I think this is the plan, right?
Yeah.
I think there was a good idea, and then the algebra gets really tricky really quickly. It's a cool method because it's like having two sorts of for loop stuck together. A for loop inside a for loop, where first I'm adding up across the columns, then I'm adding across the rows. Why is there a 1 here? Well, sort of because the area of this tiny little square is just dx multiplied by dx multiplied by dy, not multiplied by anything else. It's just those things together. I suppose maybe I don't need to write anything at all here. I could just integrate dy, but it makes me feel weird to not have anything at all. So I've put the number 1 in to remind myself that I do have to do an integral today. Okay, right, I think that's the plan. We'll integrate from y at the bottom up to y at the top. First integrate up this column to add up the little areas of these little squares. Each square has kind of got a trivial 1 times dx dy area. Add up all of those ones and then add up those rectangles. I think that's my university plan.
That is your university plan.
Okay, I'm going to cut back to your slides. Your turn. What does chat say? Why am I integrating? Okay, I'm going to your turn to put on the limits and try and work out how to make that method work.
Okay, my turn to put in the limit. Okay, so are we continuing with vertical?
Yeah, I think so. So I think I want there are some lower bounds. Naught and root x. This will let us do the green bit, won't it? The green bit of the integral. So we've got some.
The green bit. Okay.
Yeah. I guess we're splitting into the green bit and the purple bit, like you said. But for the green bit, we're going to have to integrate 1 dy by dx up from y equals 0 up to y equals root x, and then sort out our x integral.
Okay, perfect. Well, we have James to correct. Our lecturers always say this. We have James to correct our very deliberate mistake. So we have the green bit now. So this would be the y equals square root of x again, and then the x-axis. So we are taking integrals downwards. So we should be able to do this. We could do this the double integral way. So if we have double integrals, so we have a dy first and then a dx. So for the dy limits, we would take one of these little strips. So it would be a y equals x minus 2. And then, no, it would be a y equals 0 as this lower one because it's the green one.
The lower bound.
Yeah. And then at the top, it would be a y equals square root of x. And then in the outside integral, if we have a look at where this green strip is going, so we're going from an x equals 0 to an x equals, you can work out what that is, but that would be an x equals 2. So we can do the integration now with the 1 that James mentioned. And yeah, so we can x equals 0, x equals 2, start inside, and then work our way out. So dx, and then this would be y because it's dy. And then the limits y equals square root of x, y equals 0, which is equal to the integral between x equals 0, x equals 2, square root of x, and then a dx. So now hopefully we have the right value. So, oh, look, if you completely forgot about like the mess I made and then the university method at all, that would have been the way that you would have done this one anyway. So we've gotten there. So this would be, we can write this as x to the power of half, so x3 over 2, and then 2 over 3.
Hopefully we get 16 over 3 again, I think. Oh no, not 16 over 3 for this one,
No,
because we're only going up to the line.
Yeah.
Sorry, ignore me.
Okay, so we put that in, and then 2 over 3 multiplied by that, what would that be? That would be a not very nice
2
number.
root 2, I think.
2 root 2.
Yeah, sounds about right. Okay.
Which makes me doubt that answer. Is that right?
No, it's fine. The purple bit's gonna get rid of the root 2s, I think. So the cool university method for this one feels a little bit silly because you have this idea about adding together the tiny squares to make the rectangles, and then the rectangles got the limits on, and then you add up the rectangles, and halfway through this working, after setting up the problem and learning about double integration, halfway through, Lucy's got down to, integrating square root of x between some x limits, which is exactly what you would write down at A level if you wanted to find the area under the square root of x. Because at that point, both of us are working with rectangles. At A level, you learn about adding up that area under the curve, between the curve and the x-axis. Maybe as some rectangles, maybe there's a rule for it, of how to do it. Here, we put some squares in, but then we added up all the squares to get the rectangles, and our rectangles are now what you learn about at A level. The strength of this university method is that it also lets us work out that tricky purple area, the one where there's a curve on top of a different curve. So that instead of finding the area just underneath a curve, which is something we learn to do at A level, the area between the curve and the x-axis, we can find the area between two different curves. Okay. Yeah, people in chat already think maybe it's better to see the previous method. Somebody would like a more complicated method, where we can use this method. I think we've got more complicated things coming. We're going to build up to it. Should we try and do the purple area using a similar method, using this slightly more advanced method as well?
Yeah, sure.
So I've got to remember this one's turned out to be 2/3 times 2 root 2, and we sort of rub out all the green text. Maybe there's space to put in some purple calculations.
Yeah.
Meanwhile, I'll read out chat. So somebody suggests, is it better to use the previous method? At the moment, they're the same, except this one's got extra work in it. So at the moment, yes. This new method about adding together little squares is a more generalised way to think about it. That's going to let us work out this purple area. Last time, with the A-level method, we kind of avoided it. We did a normal integration. We subtracted a triangle. We brought in our knowledge about triangles. You kind of got lucky by knowing about triangles, I guess. And somebody else has asked, could we generalise this to 3D? And there the answer is yes. It generalises really well. Maybe we'll talk about this later or put something in the further reading. Okay, Lucy, we've got some integration first with respect to y and then with respect to x to find out this purple area that we avoided in the A-level approach to the problem. Let's go.
Yeah. So we have our dy dx, being extra careful to get these the right way around. So with the purple one, the only thing that really changes between the purple area and the green area are the limits. So for the purple area, our limits would be, for the dx on the outside, it would be a x equals 0 and an x equals, no, it wouldn't. X equals 2 and x equals 4. Yeah.
Yep.
And then on the dy on the inside, it would be, so as you can see, like the top limit would still be the y equals square root of x, whereas this bottom part would be y equals x minus 2 this time, not this part. So we can compute this again. I'll just do that quickly. Take the definite, so that would be y, x equals square root of x, y equals x minus 2, dx, So then that would be x equals 2, x equals 4, square root of x, and then minus x plus 2 dx, which is equal to this x to the 3 over 2, 2 over 3, minus x squared a half plus 2x. X equals 4, x equals 2.
This is going to magically cancel out the square root of 2 from before, from the green area. When we plug in all the numbers and add everything together, are we going to do this live? I think we're not going to do this live, but everything cancels out, and amazingly, brilliantly, it turns out to be 10 over 3.
Everything cancels out magically, and then we get the same answer as before. Wow. Exciting.
People in chat again want the explanation of why we're integrating 1, and I think it's a bit of a red herring, I guess. Like in school, you learn to integrate y to find the area under a curve, but it's not actually obvious why you're doing that. Why are you adding together y values? Here we're adding together the most basic unit I can think of, which is just a little bit of space, with width dx and height dy. It's got area dx dy. So those are the things that we're adding up. A little tiny thing with width dx and height dy. Oh, there's one. With width dx, tiny little bit of x, and a height, tiny bit of dy, and we're just adding those together. We're writing 1 to remember that there's nothing else there, but those are the little things that we're adding up. Along the way, I think we've proved a fact that some people say in chat. Some people in chat say that they know a rule for integrating between two different curves, that you take the difference in the functions. You do f of x minus g of x or something. You integrate the difference between root x and x minus 2. I think, Lucy, is that something that you did at school as well? Do you know that rule?
Can you repeat the rule, sorry?
So, in general, there's this thing when you've got a function on top of another function. Some very advanced people in chat know a rule where to find the area between those curves, you subtract the bottom one from the top one, and you integrate that.
Oh, okay.
Right. It's I think a thing that some A-level people just get told at some point. We've actually proved it on this board, secretly. You can't tell because we've done a particular calculation. But if Lucy points to that middle bit, where there's y in square brackets, and we've plugged in the top limit and the bottom limit, that bit, that's a proof of y is the difference between the two functions that you do. Because that's what's happening in here. In general, you're integrating 1, the most basic thing for these little units. You're integrating them between your y limits, where your y is your top function, the other lower limit is your bottom function. That gives you the difference between the y values. That's why we do that. So some people, it turns out, were taught about this at A-level for the difference between functions, and they're, I guess, still not impressed with our university methods. Maybe they knew this trick for working out the purple area. So this was labelled as cool university method, but I guess it's not cool enough.
I think some of you might not be thinking that, because it seems almost harder than the other method that we did in the last slide. So you might be thinking, like, what's the point of doing that? Well, I'll now show you the very cool university method, where I feel like you've all memorized this sketch by now, but this is it's a sketch. And instead, we'll be taking lines this way. So we'll be dividing it like this, which is what I think I accidentally did last time. But yeah, this time we actually want to do it like that. So we're going to be calculating the dx as the inside integral and then the dy as the outside, because we're now dividing it horizontally. So our integration will look something like, we have the 1 again, and then if we consider one of these little strips, this is now going between, so the lower limit, which is almost like the left limit, so this one. You can see that that will be the y equals square root of x. And then the upper limit here, this time we don't have to split it, which is good. So the upper limit is y equals x minus 2. So because we have a dx though, we have to do something else before we can find the limits. So we have to get it in the form x equals. So the top one will become x equals y plus 2, and then the bottom one would just be x equals y squared. And then the dy, well, we're taking these limits, these like little strips, all the way between y equals 0 and y equals 4. So if we calculate this now, this time we're integrating with respect to x first. So let's just keep the y limits as it is.
I'm going to let you calculate. I'm going to talk over you while you calculate.
Yes.
Here we go. This is the advantage of little squares, right? If you've got rectangles, if you're thinking about rectangles, there's only one way to add them up. You've got a row of rectangles, you've got to add them. If you're thinking about a grid of little squares, then you've got choices. You can do the previous thing, where we added them up and made them back into rectangles and then added the rectangles. Or you can add them sideways. And if you add them sideways first, and then add those horizontal rectangles together, it turns out that for this problem, the algebra is much nicer. Because, I guess previously Lucy had to split it down into two different parts, a left bit and a right bit. But if you rotate your head 90 degrees, then it all looks like one bit of range. So the strength of this method is going to be that you can do everything in sort of one big calculation, which Lucy is doing now on the screen. I've hidden chat again, so there we go. Is it going to be 10 over 3? Or
oh, it's the suspense.
Possibly.
It's like, have I messed this whole thing up? Or, oh, why is there an X? Oh, no, that's meant to be a Y.
I haven't asked, I can't tell at all if chat is impressed or not with this as a method. I'm going to let you keep calculating. So I guess the choice here is, before we were writing it down dy, we had dy on the inside. We were going to do our integration with respect to y first. With respect to y means adding up like in the y direction first. And then on the outside, we had the x integral. With respect to x means adding up along the x direction. But we could choose instead to add together those little squares, to add them together first adding up in the, oh no, I did the wrong finger motion there. First adding up in the x direction, and then adding those rectangles up in the y direction. I think your limits are fine. So it's just a matter of plugging in the number 4.
It is about plugging it
16
in.
over 2 is 8 plus another 8 is 16 minus 64 over 3. 16 over 3 is 48 over... Seems like it's negative.
It does, right? That's what I was just thinking.
What have we done? How has this happened?
Oh, it's a
Y is only 2
Y
at
is
the top,
equal
right?
to.
Y
Yeah.
is only 2 all the way
Y is
through. Yep, and somebody in chat, because of chat lag, somebody in chat has just, let's put credit where credit's due. I should always be looking at chat.
They got it before us.
They
It was
got it
just
before us. Top limit should be 2, because it's the Y value at the top. It's the thing about integrating sideways, you've got to rotate everything in your mind. Always turn everything sideways, read off your coordinates. If we look back at our previous numbers, it's weird that we got minus 16 over 3.
Yeah,
I
it
agree with
just
Tia. With the wrong upper limit, we would have got minus 16 over 3. Arithmetic is hard, says Darishlane. Good. Right. Cool. Okay.
Perfect.
We got some banter about different levels of university course going on. Cool. Okay. I think we're going to get, how do the limits work? Do you want to quickly say where your limits came from again for this time? Maybe label them on the picture so we can get them there.
Okay. So the limits. Okay. So let's try very hard to get this right. So let's say this is like the origin, obviously, and then this one is 2, 0, and this one is 4, 2. So with our limits, with the dx limit, so the x equals y plus 2 and the x equals y squared. So those are, because we're taking these, if we just look at one strip, so let's change color because it's very red here. Okay, green. If we just look at one of these strips, then the lower, it's like bounded below by this curve, and it's bounded above by this curve. So that's where these limits have come from. But because it's a dx, then we need to have it in the form like x equals something. So with the other one, we now have one strip, so which, like, this entire integral forms one strip. And we need to take these strips all the way between here, all the way up to there. So that's where the y equals 0 and the y equals 2 came from, not 4, because that's x, so y equals 2.
It is the same. It's the same idea as before to do some of the squares to make rectangles and then some of the rectangles. But because we've turned our heads 90 degrees round and we're changing everything round, everything has to switch round. Somebody's asked if they can get marks for doing this in A-level maths.
Yeah.
Alfie says I was rotating my head the wrong way. Okay. I'm trying to match it in that. I've got to do that. There we go. Everything makes sense now. Okay. Very cool university method. So this idea about writing your areas in a different way, rather than writing them as just the integral of y, boring, write them as the sum of lots of tiny squares, gives you this extra flexibility, this extra idea. Lucy, I think you've got another more tricky problem, which I think we might put in the further reading for people to try.
Well, yeah. And then we'll move on to the probability. So, before I show you it, I just want to show you a warning. So I was 2 a.m. Lucy on Espresso thought that it would be a good idea to include the next just as like a way that you can use all the techniques that we've previously covered to solve something hopefully interesting. So I created this picture using graphs. So this is a parabola in the form y. So you can think about which way you take the integrals, think about how it's bounded, and then down here, again, we have parabolas, but these are in the form x equals something. So think about which integration method you'd use, the cool one or the very cool one, both ways. And in case you can't tell, it's meant to be James. I should have filmed James' reaction like the first time that I showed it to him, because he described it as like, what did you say, like a weird robot person?
Yeah, like a weird robot person. And then I realised I was describing myself. Cool, right. Here is a challenge for the further reading. Oh, if I put this in the further reading, it means I need to upload this picture to the official departmental website. So that's happening later today. We've got this for you to work out the area of my face. And if you can work out the area of my face, given these edges of where it is in terms of x and y. Thanks, Lucy. That's properly horrifying. Molly got it first. Molly at the bottom of the chat. Is that James? LOL.
She probably got it before we said it.
Yeah, chat lag. We always appear to be first, but not how that works. Right, cool. Okay, that's going to be an exercise to practice doing, so you can practice maybe doing this double integration idea, both in two different directions, to see if the cool method or very cool method is actually helpful. You don't have to know this for A-level maths, obviously, or for GCSE maths. I wonder if the people who were GCSE are still here. If the GCSE people are still here, hey, you don't have to know any of this at all. And we had a little chat in the chat about whether you could still get the marks for doing A-level problems like this. I reckon you probably could, but you definitely don't need to know this for A-level. This is a hint of something that's coming up in A-level. Should we do the probability input?
Yes,
people are changing their names in chat. It's all getting out of hand. Can we get this off the screen and talk about probability?
Yeah. Oh, we've got it again.
Oh no.
Probability. Okay. A probability problem is that we have two dice, as you can see here, dice 1, dice 2. And if we roll them, both of them, they're going from 1 to 6, standard dice, and we want to find the average difference in like what values you get. So if you get like a 2 and a 6, then the difference would be 4, as an example. So how do we work out the average of all the differences that you could possibly get?
I think this one we can give them a minute to try it.
Yeah.
And also because of chat lag. Completely different problem. We've got a probability question. We'd like to know the average difference. I guess the difference between them is always positive?
Yeah.
Yeah. Okay. If they're the same, it's 0. If they're different, it's some positive number. Okay. Yeah, so people who are saying 0 in chat are possibly thinking about negative numbers.
Yeah.
Okay, clarification. The difference is always positive or 0. And there's a guess about my number 1 fan thinks the answer is 7. I don't think the average can be 7, because I think the difference is at most 5 for what could be. The most different numbers would be 1 and 6, right? Ali wants to use entropy. I don't think we need to use entropy for this. I liked whose suggestion was it? Alfie? Alfie wants to draw a table.
That sounds like a good idea.
Yeah. Alfie's going to have a go at drawing a table, I think.
Okay.
What you put in your table is, I guess, a different question. People think it might be. Oh, Tia's got a guess. I think it's a guess because it's got a question mark on it. 2.5 for somewhere between. I guess thinking about how. I don't want to put words into what Tia's saying, but 2.5 I think is. 2.5
Maybe
is like a half of 5 because the difference could be 0 or it could be 5. 2.5 is somewhere in the middle. Kind of feels about right. People are guessing 2.5. Seems quite popular in chat. My biggest fan wants to put 3, and Raphael says the average is 7 when you add them. You use that. It's a tricky question. It's not obvious what the answer should be.
Can we go into the table then?
Let's do a table.
Let's do a table. Okay, so someone suggested that we do a table. So if we have like a two-way table thing. Okay, so if we consider the first row along this axis, so we have like 1, 2, 3, 4, 5, 6, and then the second row along here, so 1, 2, 3, 4, 5, 6 again. And if we consider the difference, we can just like fill it in. I'll just quickly do that. So we can form like, it forms like some like diagonal thing. James, if you want to say anything, it might take me a while to fill this in.
Looks good. Carry on, Lucy. It's going really well. We work out all the possible differences. Sometimes this is the best way to do a probability question, is to just think about all of the possibilities, and there are only 36 of them. We're going to just add it all up. That's a 3, right? Add them all up and work out what the average difference is divided by 36. Okay. Oh, somebody's in here. Somebody's got a number, an anonymous person. I've hidden it from the stream right now because it's over the top of Lucy's grid, but I think the number that you've just posted in chat, I think is correct.
Okay, so we've got our table and we filled it in, and then we can just like add up all the values and then divide by the total number, which is 36. So total value over 36 would be our average difference. So did you say someone worked it out, James?
Yeah, it turns out the total of those numbers in that table that total is 70. adding fans in chat today. I've got some tricks for doing that addition. I don't think we've got time to do them live, but I've got some tricks for doing that addition that I might put in the further reading. So how would you add together all those numbers really quickly? It's something that I tried to think about. I'll put something in further reading. 70 over 36, cool. Which is a little bit less than 2, which is maybe surprising. Because 72 over 36 would be 2, so it's a little bit less than 2. Smaller than we thought, right? I guess that means your intuition of how different the dice are. Anyway.
Okay, should we move on to a different method then? So we'll notice that this is 2, and we'll also observe that it's around like approximately a third of 6. So that seems a bit random right now, but we'll see where that becomes useful. So we have an integration problem now. And I'm just going to put it out there that this is what I'm studying right now. So it's on the multivariable calculus course in the Hillary term. And I had my tutorial on this yesterday. And my tutor specifically said, like, don't do this problem. So let's have a go. So you have double integral between 0 and 1, because no one got this right in the tutorial. X minus y dA. And we're trying to work out what this is. So if we rewrite this into like a form that is actually understandable, is x equals 0, x equals 1, y equals 0, y equals 1, and then x minus y, dy dx. So we have an integral now, and it looks like in a similar form to the ones we did at the very start, except for the fact that there's like this absolute value there. So it's not absolute value. I don't know if any of you know like how to integrate it, but it's not the easiest to integrate. It's not like a standard integral. So yeah, let's see how we will deal with this. Shall I give them a few minutes or just like go into it?
Just say that, okay, if you have your dA is equal to, yes, we've got this integral to do. This is one that we give to the first years. I'm also a tutor for this course. I told my students they had to do this one. Does that make me evil? So doing this sort of practice problem, here we're integrating something different. This is related to some ideas from probability. I think Lucy's going to say this in a moment. Are you going to explain this link to the probability thing?
I'll leave that to you. That was the
Okay. So how I would do this question, so maybe they're having a go, I don't know. But how I would do this, we're integrating, I guess the power of this new thing is that we can integrate functions. We could put a function instead of the 1 in there. All those people saying, why have you got a 1 in there? That's just the rule for areas. The area of a little square is the area of a little square. But we can integrate a function if we want to. That function inside depends on x and y. So that's a bit tricky. I would split it up, and I would just think about the half of the world where y is smaller than x. So I would just think about the bits where y is smaller than x, and I would remember to double my answer at the end. So I think I'd think about whenever you've got problems with an absolute value sign in, sometimes it's helpful to split them up into bits. Like case 1, maybe the thing inside is positive, or case 2, maybe the thing inside is negative. If you do that, then you get you can take off the absolute value signs. You've now understood in each of your cases what the thing that we're trying to do is. Right, so on this first one, Lucy, on this one you've just written down, I want different limits because I want x to be bigger than y.
Of course, yeah,
so I think I want
this one becomes
y to be only go up to x. So this is my way of splitting down the integral, I guess. That I want to say, okay, I've got this absolute value sign, it's a real pain, I don't know any rules for integrating absolute value sign stuff, but if I just take my y integral, the limits on my y integral, and I stop when I get up to x, then I know what's going on in there. Y is small, so the absolute value of x minus y is just x minus y. That's an integral I can do. I mean, it's a double integral thing, and there's some different terms going on. I've got to integrate with respect to y and then with respect to x, so it's a little bit of a pain, but there's something I can do. And the other one there, the other term that I'll get, is pretty similar, but I guess it's integral from x is 0 up to 1, and integral from y equals x up to y equals 1. The rest of the world, the rest of the y values, from x up to 1, and I'll integrate y minus x for that bit. Cool. So I'm splitting up my y integral like that. If you do that, then you've got some integrals to do, and the numbers work out so that the answer to this double integral thing, integrating this random function across these values of x and y, turns out to be exactly 1/3. And the question that we asked our undergraduate students is, what's this got to do with probability? So the whole thing overall is 1/3. What's this got to do with probability? And what's this got to do with the dice thing that we just did? Lucy, what do you... I don't know if you thought about this part of the question, so hey, live. What's the link to probability?
Yeah, so we calculated that the integral is 1/3. So going back to like the dice question, I guess like it's all linked in some way. So the mean distance between 2 points. So basically, what this integral is saying is that the mean distance between, if we pick any 2 points, if we choose them randomly, from the interval 0 to 1, so we can only take x between 0 and 1, and we can only take y between like 0 and 1. So if we pick any points in here, randomly and independently, so what you pick for the first one doesn't affect what you pick for the second one, then this integral is saying that like it's 1/3, like you will as a whole like get the distance apart being 1/3. James, do you want to add anything?
Yeah, so this is just like the grid, SV's just said in chat. This is just like the grid for the probability dice rolling problem. When we showed you the grid problem, what people suggested was draw a table and try and think about all the possibilities. There are 1, 2, 3, 4, 5, 6 things that the first dice could be, and there's 1, 2, 3, 4, 5, 6 things down the other side. And that's like a discrete probability thing, where you've got these things, and the answer is you're supposed to add up all of the little numbers that you've got, and then divide by the total area, 36 squares or something. This is the continuous probability version of that question. This is the version to say, if instead of having discrete probability, 1, 2, 3, 4, 5, 6, what if I've got a continuous random variable probability? anything between 0 and 1, what's the average difference between two numbers chosen between 0 and 1? Which is the sort of continuous version of the discrete rolling six-sided dice thing that we did before. And here the answer is much nicer. It turns out to be exactly 1/3 in this continuous case. So this is 1/3. Great question in chat. Why wasn't it exactly 1/3 before? Why wasn't it exactly 1/3 for six-sided dice? That's a really good question. I think the answer, one way to imagine the answer is that, with six-sided dice, everything's quite blocky. The kind of distribution of what the difference could be isn't a smooth distribution. It's kind of blocky and like a bar chart with different things that the distance could be. But because it's blocky, it doesn't quite have the same answer as this smooth, continuous, lovely version of the question. You can get closer to being 1/3 of 6 by changing 6. That didn't make any sense. So you can get a better approximation to this 1/3 fact if you do the discrete problems, so six-sided dice. If you play Dungeons and Dragons, then you're aware of other dice. If you saw Platonic Solids, the episode 3 weeks ago, you're aware of other dice. If you tried for other sized dice, you draw a bigger table for a discrete problem with dice that have got more numbers on, then you get an answer that is closer and closer to 1/3. It's a bit like having a bar chart that gets smoother and smoother as you put more and more sides on your dice, until eventually, in this nice continuous case, it's like having a very smooth distribution of what the difference could be. Cool. Okay. So this is a correspondence between double integration being kind of the right way to do continuous probability questions where you've got two continuous variables in there. I was really good at application of this stuff. With some links back to probability theory that you learn in school. I think we've got lots of ideas for the further reading stuff as well. Lucy, was there anything else that we should have said about this problem or about double integration?
Nothing about double integration, but I was looking through chat when you were speaking just then. And I saw that Mun Robot came back, and that was a joke that was there when I was watching.
Yeah, so Mun Robot is a portmanteau of my surname and the word robot. Is that top chat? Is that top chat at the moment?
I'm on the recent. Let me see.
Pretty well on top chat. Cool. Oh no, top chat is don't mention the mat from Molly. Sorry Molly that I mentioned the mat earlier. Okay, I think we've shown you double integration as this weird idea that you can go one step more granular than the sort of integration you learn in A-level. So you learn about adding rectangles, you can go one step more abstract to add together tiny squares. And we can take that in lots of different directions, literally. We can take that sideways, we can take it up and down. We can go to 3D and think about adding little cubes in 3 different directions if we want to do some sort of volume of some region. It's a really versatile method that also lets us integrate just random functions across different values of x and y, and just how you do continuous probability with more than one variable involved. But I think we're going to leave the maths there and wrap up. What do I say at the end of a live stream? Can't really remember. Let's quickly take things from chat just to see what else I missed. Somebody wants another probability example in the further reading. I will have a go. Give you another calculation. We've got that picture of my face to integrate, to practice doing some integrals sideways as well as up and down in the normal way. And there's something going on to do with maybe like normal and binomial distributions. There's lots of stuff in probability where you've got like a discrete variable, but if you make the number of samples or the number of possible outcomes really large, then it starts to become more and more smooth. It's sort of like the same idea behind calculus about approximating things more and more. And there's requests to recite pi, which I think I've done before. And the Mat livestream, somebody's just said, is there a Mat livestream? Mat livestream starts again in August 2022. The Mat livestream is a bit like this, but I guess less relaxing. Sorry, Molly. Less relaxing because it's just talk about Mat problems. We'll just do some maths. But that's coming back in August. Oh my word, is that a Desmos? Oh my word, hang on. Somebody's put it into Desmos. Have they actually? Or is this
oh no.
This is a real thing.
It's going to look even worse on Desmos.
They've done a different picture.
Okay.
Can I
Alright,
get this on stream?
Do you want to share your
I'm going to try and get it on stream. Just because it's horrible and amazing.
Oh,
Somebody's just sent in
Pythagoras.
this.
Sorry.
Hang on, I'm trying to get it on screen.
Mhm.
There we go.
Pythagoras.
Somebody's just sent us this. Link in chat somewhere near the top of their attempt at drawing my face in Desmos using, oh my word, so many different sorts of parametric plots and equations. I find these things really terrifying. Right. Thank you, chat. Thank you, Lucy. Thanks for coming on. All the best with the rest of first year mathematics, and maybe see you on the stream again sometime. Is this the same as this is the same as was described earlier? It's the same, but with. Oh, I'm very confused now. Okay, right, good, right. On that note, I think we're going to wrap up the stream here. Thank you very much for watching. We'll see you next week for another episode of the Oxford Online Maths Club. It's bye from me and bye from Lucy.
Bye.
See you around. Take care.